my friends, and welcome back for the second video on the forces. We're going to focus today on motion and motion graphs to begin with, then we're going to move on to moments and pressure, and then we're going to finally look at momentum and braking and stopping distances.
So we're going to go on to looking at describing motion and how we can do that, which usually comes down to using graphs. So we're going to start looking at using graphs. We're going to use a couple of equations here too, but we're going to start off by just considering a difference between speed and velocity, which relates to scalars and vectors again. And the equation that we need to know here is the old equation you might have learned way back in primary school even, which is distance equals speed times by time. You can rearrange that, and we're going to change some letters too. So if we change some letters here, we can change distance for displacement, which is an S, and we can change speed for velocity times by time. Now that's a much better equation to use, again, because in physics we're talking about vectors that need direction and magnitude, and so velocity and displacement both have direction and magnitude, whereas distance and speed do not. So in the equations that we start using from this point onwards, we will be using the letter S, but it will be the letter S in the form of displacement. So that is in meters, velocity is in meters per second, and time is in seconds. That's a really good start point. So velocity is a vector, so again that has a magnitude and it has a direction, whereas speed just has magnitude. And that's basically the importance of it. You might have done in class, you might remember some things like going from A to B, if you considered an object that was going from A all the way around to B in some crazy form, and then you had the displacement of it would actually just be a direct line from A to B, whereas the distance would be the squiggly. Speed can be considered the same. If an object had a constant speed going along the squiggly line at 70 miles an hour, its overall velocity would probably be, 50 miles per hour, something like that. So they're very different values, and very importantly different in physics terms. The higher tier bonus kind of consideration here is the idea of explaining that basically in circular motion. So if you have an Earth, for example, is orbiting the Sun, its speed is constant in circular motion because its speed is the same. Actually, it's not true, I know. For this orbit, it would definitely be going faster as it's getting faster closer to the Sun, and it'd be going much slower when it's up here. But ignoring that, if it was a perfect circle, you had your Sun, and it was going round in a perfect circle, just like this, it would have a constant speed, but its velocity would be always changing, because if we were considering velocity in this direction, once it's coming back from here, it would have the absolute opposite. It would be negative velocity. At this point where it's travelling in a dead horizontal line, its velocity would technically be zero because it's not travelling up or down with any velocity at all. So that's quite an extra important consideration. That's a little higher tier thing, and you just need to be able to explain qualitatively, which means just with words, with examples, that the motion in a circle involves a constant speed but a changing velocity. And the first kind that you'll have to use is a comparison of distance and time. And this tells us a few things. So for example, you can see here that the distance is increasing at a constant rate, which means that the object must be moving with a constant velocity. The constant velocity part, we know that because every second it is increasing by the same amount, or even every 3 seconds it's increasing by 5, so you could work out there its velocity pretty nicely. And to do that, you could do it really simply. Velocity is measured in meters per second, which is meters displacement per second, second being time. So it's the displacement, which is S, remember, divided by time. And to get that from the graph, it's actually the gradient. So it's the gradient of this graph quite nicely. So you could actually take a gradient of there compared to this. You could work out that that's a distance of 10 and it's a time of 6 seconds. 10 divided by 6 gives you your velocity. At this point here, we've got a nice flat section of the graph where the distance is actually 10 and it's staying at 10. It's a constant distance. So velocity there must be absolute zero. Remember in the previous slide, it might not actually be stationary, it could be moving perpendicular to it, 90 degrees to the direction of travel that we were initially looking at. And then in this graph, it has a not so constant rate of decrease here from distance, where it's actually moving back to the part of origin. So we've got an object that's moved away from us, it's stopped, then it's moved back towards us. The extra part, though, is a higher tier consideration, is something called working a tangent. So when you've got a line like this, which isn't actually straight, it's curved. Let's look at this a different way. If we did a curve like this, which would be a much better representation of acceleration, we need to be able to work out the velocity at any one point on there using a tangent. Okay, and what you would have to do is find the point that you want to work at. Let's say you want to find the tangent of the velocity at this stage, at this point. What you would do is you'll draw a straight line across that point and work out the gradient of that line. And that's an instantaneous velocity, if you like. At that moment in time, what is the velocity there at that stage? And you'll have to do the same in chemistry for rates of reaction. And it's just a good skill to have. You definitely need to do it in maths too, if you haven't already. Acceleration is a change in velocity. Change in velocity over time. So a better way of describing that would be the rate of change in velocity. There's a little equation we need to know here, which is acceleration is equal to the change in velocity. So delta v, change in velocity. That delta symbol, if you haven't seen it before, means sorry, this triangle symbol there, that means change in, so it's a change in velocity divided by time. Technically it should be delta v over delta t. It's also a change in time, and that's something we need to be able to calculate. So if we've got a change in velocity, like a change in velocity on a graph here, so we've got a change of however much velocity this is, we can work out its acceleration by comparing it to its change in time. And this is its gradient. So the gradient gives us acceleration on a velocity time graph. That's a really important little bit. So we've got here a gradient that we could work out. We could also work out a negative gradient. So it would be a negative gradient because we've got a minus change in velocity, so let's call it minus 10. Time is going on for 5 seconds or however long. But that directionally would be a negative acceleration or a deceleration. We've got here the velocity being constant. So the velocity is constant, acceleration must be constant too, because it's not changing its velocity. Forces, for whatever reason, must be balanced, no resultant force. And the other thing that we can work out, though, is the using the area underneath the graph, and this is quite a cool little thing. So typically you get a graph that's got squares on it. If you count up the number of squares of those, when we work out the area of that space, the area is going to be the length times by the width, or the, in this case, time multiplied by the velocity. And if you get time multiplied by velocity, it gives you displacement, because you've got meters per second and you're multiplying it by seconds, which cancels out the distance, the time, and it gives you displacement, which is meters. So the area under the graph, which is the higher tier scale, just to calculate the area under the graph, it's a higher tier scale. It gives you displacement. How good is that? But these kind of graphs are not typical, because usually you don't get this kind of perfect straight increase in velocity, which is a constant increase in velocity, or a uniform acceleration, uniform motion, because it doesn't really happen unless you're skydiving, and for the first part you have no impact really of air resistance, because there are so many other forces at play. So most of the time you see a curved increase. So this graph down here, you can see how the velocity is increasing rapidly, slows down, maybe the car changes gear, and then it starts accelerating again. But it's not constant acceleration. It's not that. But uniform constant acceleration is g, for example, is constant acceleration, accelerating at 9.8 meters per second. And if you looked at the gradient here, perhaps of this graph, and you looked at this part, perhaps it would give you 9.8. But typically you can see then it's curving off, it's no longer uniform, it's reaching terminal velocity. So describing uniform acceleration, as we've just said, this is where the acceleration is at a constant rate. So constant rate of increase of increase in velocity, or it might be a decrease, I suppose. But it is a constant, it's not going to change, and this is where it doesn't really always work, but it's a great little equation that you'll use more if you do this at A level. But this is an equation that you're given. It's one of the Suvat equations, which is v squared minus u squared equals 2as. And what we've got here, if I get rid of this, we've got some space. V and u are descriptions of velocity at different points in time. The way that I tend to remember it is if you put these two in the order of the alphabet, u comes before v. So v is the final velocity, so that's the end velocity in whatever section of experiment or you're looking at, and u comes before v, so u is the beginning velocity or start velocity. So we're looking to calculate the change in velocity first, so that actually is delta v, but it is squared, so we have to keep it as it is. And we've then also got 2 times by acceleration times by displacement. So that's acceleration and that's displacement. That's really important that we don't get s as time or speed, because it's not speed. We've already got speed considered as velocity because it's directional twice before. You'll only ever be asked to put numbers into this equation. You might have to do a calculation before or after having used this equation, but you'll be given clear information of how to do that. Hopefully it won't be too complicated. But the only thing you might fall short on is remembering that this is squared, so you might have to square root the answers that you get, or the numbers that you use. But quite often v or u is 0, so you'll be starting with an object that's not yet moving, so you're starting at 0, or you're ending up with an object that is going to stop, which ends up being 0. It's all good. Terminal velocity is the other consideration we had on the slide just previous. This is where you might end up with a skydiver. Let's say a skydiver is happily jumping out of a plane. He's got a constant weight, and then you've got the skydiver still. He's got a still constant weight. I'm just drawing his head because it's so much simpler. I can't draw. So his weight is always the same. So weight, always the same, because he's not gaining mass. He's not changing his g, gravitational field strength around him. But what will change is as he starts moving faster, he's going to get more and more and more air resistance developing. So he's jumped out of his plane, he's getting faster and faster and faster. When these two forces are balanced, when he's going so fast that his air resistance has ended up equaling the force that's pulling down his weight, so when his weight and drag, let's call it, are equal, he's no longer going to accelerate. He's not going to accelerate anymore. It's just going to stay at a constant velocity. And that constant velocity is what we call the terminal velocity. Terminal meaning the end point. He won't get any faster than that. He could get faster if somehow magically he gained mass or he reduced his air resistance, which can be done. But that's what we call terminal velocity. If he then opened his parachute, you'd have whoosh, this is going to increase way more his air resistance. And he's going to slow down, and he's going to slow down until he has got a little bit slower. So his air resistance might be a bit higher than his weight now. Air resistance might be only just a little bit more. Eventually they're going to get equal, and he's going to reach a new terminal velocity. So here we have not an actual force, but an effect of a force, a result of a force, if you like. And this is something called a moment. And a moment is a turning effect of a force. And we should be able to describe examples of where a force causes a rotation. We do need to know an equation here, and I like to think of moments as a multiplier of a force. The other type of effect of forces that we'll look at is pressure, which is also almost a multiplier effect. But in this case, the equation that links to it is m for moment equals F times by d. So the force itself multiplied by the distance from the pivot. So that's going to be in meters. Force is going to be in newtons, and a moment doesn't have its own special unit, it's just a Newton meter. If you can remember that, again it gives you your equation because it's n times by m, which is equal to F times by d, which is exactly what the equation is, and we need to just know that. So it is a turning effect. It's caused by a force, and it's going to cause the object to spin. So we have a lovely example here of two gents sat on a seesaw. You can see the gent on the left is slightly larger than the gent on the right. So it's usually a good opportunity to link to the example of weight, where weight equals m times by g. So g in this case is exactly the same, but the mass of these two gents is different. But actually in this case we've got a seesaw where they're both causing a force to go down. One is causing a greater force than the other, but one is also a shorter pivot distance from the pivot than the other. And in this case, for them to not be tumbling down to the ground and causing the seesaw to move, their moments must be equal. So the Newton meters on one side are the same as the Newton meters on the other. Or a way of actually writing that might be m1 equals m2. So m2 being on this side, m1 being on this side. And if we expand that a little bit more, if we expand it to use the equation itself, you could say that F1 times by D1 equals the F2 for the right hand side, the force for the right hand side, equals F2 times by D2, and they are the same. And using that principle, we can then solve a lot of problems. So for example, if we knew this chap's weight on the left, and we knew the distance from the pivot, and we knew the distance of the chap on the right from the pivot, but we didn't know his weight, we could work that out. And of course, if you wanted to turn this into a lovely 5-mark question, you could take that weight and they could ask you to work out his mass. So then you'd have to take the data you just collected, the data you calculated, and apply it to a different equation, which is nice. We like those kind of things. Another example of what they might ask you to do, so looking at the top right here now, for this crane example, we should do here really is we should try and put in our equation from earlier, so that F1 times D1 equals F2 times D2, to try and work it out. So we know the turning force on the right hand side, or at least we should do, because we've got here the D2 and we've got the F2, we've got the D1, but we don't have the F1. So if we put that into an equation, we should have F1, which is what we're trying to find out, times by D1 equals F2 times by D2. And what examiners will like you to do is to write out the equation as we've done here, and then substitute in the information that we know. So we don't know F1, but we do know D1, so we can substitute D1 for the info that we do know. So D1 is here 2.4 meters, equals on the other side F2 is 6,000 times by D2, which is 6.4, and then we have to rearrange this to get F1. So again, they like us to do these stages. So we've got stage 1, that would be 1 mark for having the equation, stage 2 substituting in the information, stage 3 would then be rearranging it. So F1 is equal to, if we move this to the other side, we're dividing by the opposite of the multiply symbol, F1 equals 6,000 times by 6.4 divided by 2.4. You get the idea, and you can solve the problem. It's lovely. We love problem solving. That's what physics is all about. And on to the next part here. So we've got another equation, another example of question that we can look at. You've got a lovely pivot. We've got a support. So the support here is applying a force. We've got a distance from the pivot of that support. We've got the distance of the girl from the pivot, and we've got her weight. So we have, if you write out this equation again, if we call this distance 1 and F1, and then we've got F2, and we've got distance 2, and then again you go through the whole motion of F1 times by D1 equals F2 times by D2, and again solving the whole problem. So calculate the moment of the girl's weight about point A is the first question, so using just these two, and then the second question later would go on to ask you to find out what F1 would be, using the same setup as we had from the previous question.
So pressure is another example of an interaction with forces, where forces are acting and actually being multiplied or diminished. And in this case, pressure is where a force is acting at a normal or right angle to any surface. We do have an equation here that we need to know, and it's almost the extra definition of pressure, which is pressure is equal to a force divided by the area that it's acting on. Force again is in newtons, Area is measured in meters squared because it's the length times by our width. And pressure as a result, I mean, its units in a way are newtons per meter squared, which is the same as the equation, but the unit that we use is pascals, which is representative of newtons per meter squared. Again, we must have the correct units here when we're doing a calculation using pressure. So we're going to explore pressure in interacting with a surface, which just follows this rule. That's quite simple, and a thumbtack is a really good example, or a drawing pin, I suppose you call them. You've got pressure applied to a large area, so when you're pushing down with your thumb, it's not going to hurt your thumb because there's not very much pressure, because there's a large area, but you're putting down the force. The force that you're putting through is exactly the same, but when it's applied to the very point end here, sticking it with a pointy end, you've got a very small area, and the force is still high, so you've got a very small area, and as a result, you've got a tiny little small area underneath a large force. You're going to end up with a big pressure, which is good. The next part we need to consider in pressure is how pressure behaves in the atmosphere, and this is quite an interesting one. So first thing you need to think about is if you've got an object, that object is going to have pressure exerted on it by air particles colliding with it. That collision with that surface of the object is going to involve a force, and that force therefore is going to get converted to a pressure because it's acting over an area around that material, that object. Now what is important to consider with the atmosphere is that all the gases and particles in the atmosphere are experiencing a force of gravity, so they're all experiencing weight. So they're all getting pulled down towards the surface of the Earth, or towards the centre of the Earth, and as a result you end up with much more dense atmosphere at the bottom of the atmosphere than you do at the top, where air is more spread out. The particles are more spread out, and as a result you've got a very important difference in the amount of pressure that you would feel or the object would experience, and that's because simply lower in the atmosphere, with a decrease in height, you've got a higher density of air, and so more particles, and so more collisions, and if you've got more collisions you have more force, and with more force you've got more pressure. If you look at this exam question here that we've got written down, in this exam question you can see it says, why does atmospheric pressure decrease with an increase in height? So if we're increasing that height, we have a decrease in the amount of air particles that are going to be around, because you've got a lower density, and if there's a lower density there's going to be less or fewer collisions, and so therefore less force, and so therefore a lower atmospheric pressure. So to work out the amount of pressure in a body of liquid, let's say you've got a point in this tube of water that we want to consider, we have to first go back to this equation that we had of pressure equals force over area. That's the definition of pressure. When we're looking at a body of water though, we want to know how much this force is, which is in effect its weight of the water, and the area that it's acting upon will be part of what we consider and calculate here too. So we're given this equation, which is a pressure, and it's equivalent to the height of the water above that point, which is h, multiplied by the density of that water, which is the rho symbol, which is a bit like a p, a slightly tilted p, multiplied by g, which is gravitational field strength, and the units of those are meters for height, density is kilograms per meters cubed, and g in this case is newtons per kilogram, so how much force is pulling each bit of mass down. Technically the same as acceleration due to gravity, but just different units for it. So if you multiply those units together, you find that you're ending up with the newtons. The kilograms cancel each other out, and the meters cubed and meters cancel each other out down to meters divided by meters squared, so you end up with newtons per meter squared, which is exactly the same as pressure, which is measured in pascals. One thing we might have to do with this equation is looking at a person sat under the water, is consider the difference in pressure between the top of them and their bottom. So you'd have to work out the difference in height between the top and the bottom, and as a result find out the difference in pressure. So that might be a difference of 2 meters, and so the difference in height, if we're then putting it into our equation, we've got pressure equals height times by p times by rho times by g equals 2
times by rho times by g, and then we're substituting in the information that we should have for that. That's called density is 1 times by g is 9.8. We end up with the difference in density between the 2 points because we worked out the difference in height here, and that's quite a useful task. They asked a similar question in 2018. Let's consider here that we've got a body of water, and in this body of water we've got a submerged ball, a ball with a smiley face, of course. It's got to be happy. What we're going to look at is something called upthrust, and try and understand why upthrust is a thing and how it works. And it's based on the principle that most objects are not a two-dimensional flat surface. They actually have two different points of height in this body of water. So if we look at how much pressure they have at each point, they're each going to have a different pressure because the top is at a different height in the body of water to the bottom. And as a result, the amount of pressure that they actually have will be different. So H times by rho times by G, and H times by rho times by G. If this one is much lower, let's call the height, let's call it 2, and let's call the height of this one 1. If it is twice as deep as the previous, it's going to have almost twice the pressure. Well, it will have twice the pressure, in fact. So it's a significant difference in the amount of pressure, and part of pressure, remember, is force. The definition of pressure is force divided by area. So we're going to have different forces acting at these two different points on this ball. So the pressure, remember, acting in all directions on this ball. We're going to have pressure acting down on the top. We're going to have it acting on the side, we're going to have it acting on the bottom, from here on this bottom as well. But because we've just worked out that there is a different amount of pressure at the bottom than there is at the top, the amount of pressure, the amount of force that's applied at the bottom will be greater than the amount of force applied at the top. And what this ends up with, my friends, is a resultant force. So this ball is going to have a force pushing up, which is greater than a force pushing down, the pressure pushing down. It's going to have equal pushing on each side in those directions. Which is going to get counted out by that side. It's going to get pushed up more by this bottom. So as a result, its resultant force will be upthrust. It's going to end up accelerating upwards. And that is what upthrust is. It explains why boats will float on top of the water. It's why things will float underwater at a certain height. It explains why things will sink as well. So density plays a big part in whether things will float or sink. So momentum is another interaction of forces that we need to consider here. It's a higher tier skill only, and it's defined by its equation. So when they say you need to define momentum, you just need to actually write out that momentum, which is P, is equal to m times by v. So momentum is the mass of the object in kilograms multiplied by its velocity, which is meters per second. And momentum as a result is, if you multiply those units together, just kilogram meters per second. The higher the momentum something has, the more force it requires to stop it. But the definition, as I say, we don't need to actually write a lengthy sentence out or anything like that. The definition is just P equals v. That's what they want you to write. Momentum equals mass times by velocity. Writing out a word equation for it would be better. But momentum's got a very important rule to it, which is the conservation part. So momentum is conserved, and that's in a closed system. So that's where nothing is leaving the system. It's being contained in this diagram. It's shown in a circle. In these circles, the system of interest is a closed system. Nothing is leaving it. The total momentum before an event is absolutely equal to the total momentum after the event. So if you took the momenta of all the objects to begin with, multiplied their masses and velocities together, added those up, you would have exactly the same at the beginning as you do afterwards. With this assumption of momentum being conserved, we could say that P1 plus P2 equals, afterwards, we could call this now P3 and P4 equals the momentum afterwards. So P1 plus P2 equals P3 plus P4. So we would need to do some calculations for the using the idea that momentum is being conserved. And in this case, you can see you're being asked to find out the velocity of the end result of this event, where you've got two railway carts colliding. You've got their masses, you've got their velocity, and we know the mass of the carts afterwards, but we don't know their velocity. So what I suggest you do in this case, we know that the momentum before is going to be equal to the momentum afterwards, and so we can work out the momentum of the event that we know, and we can then solve what we can with the second one. So here we have two carts, each with 30,000 kilograms. For the first cart, we're going to multiply its mass by its velocity, and we're going to add that to the mass of the second cart multiplied by its velocity, which is 0. So we have here, we've got 30,000 times by 8, which is 240,000, plus 0, which is going to give us 240,000. So that's our momentum beforehand. So we can write that in here, 240,000, and the unit is, of course, kilograms meters per second. Afterwards, we know that that is going to be exactly the same. So what we now need to do is use our momentum, which is our p. We've got the mass, we need to find out velocity. So if we have p equals mv, we can rearrange that equation to try and find v. So v is equal to p divided by m. And then we can do our calculations. So we've got 240,000 is our momentum divided by 60,000 is going to give us a lovely 4. And so our answer is going to be 4 meters per second, giving it the unit. And you can see a bit of logic here. It's always worth checking your answers with a bit of logic. You've got one cart colliding with another. One is going at 8 meters per second, the other is going at 0. When they both collide, they've both got the same mass. It's likely that the speed is going to be halved, or the velocity is going to be halved, I should say. Another example that you might have, which you might have done in school, is using exploding trolleys. They explode outwards, one's going to explode this way, the other's going to explode that way. You can try and work out the mass, or the velocity that they will have. You might have, for example, put masses on one, made it a bit heavier than the other, maybe making it twice as heavy. Let's go with that. This is twice as heavy as the left one. If they explode, you can find out the change in their velocities and find out how fast they should be going. And the lovely assumption here is that because they are currently not moving, you've got a mass of, let's call the one on the left's got 1 kilogram. It's multiplied by its velocity, which is stationary at the moment, is 0. We're adding it to the velocity times by the mass of the second cart, which is 2 times by its velocity of 0. That, of course, is going to be 0 plus 0. It's going to give us a total momentum of 0. So afterwards, we know that their momenta is also going to be a total of 0. So we need to try and figure out what it is. Well, if this one on the left, let's say, is going at 5 meters per second, we can work out what the one on the right is travelling at. So the total momentum still is 0. We know the mass on the left is 1, and we're multiplying that by 5. That's velocity it's travelling at. We're going to add it to the mass of the second, and we've got its unknown velocity. Let's call it v. So if we multiply this out a little bit, we've got 5 plus 2v, which we don't know what that is, equals 0. If we then remove the 5, we take that to the other side, we end up with 2v equals minus 5. And we work out then, therefore, that v equals minus 2.5. And the minus part is really important, because this first cart, this first trolley, is going to the left, which is a positive direction of 5, and the one on the right is moving to the right, which is a negative direction. It shows again that the velocity here is a vector quantity, so the minus sign is showing us the direction. It's moving in the negative direction, 2.5. Again, error checking. The fact that it's twice as heavy means it's going to go twice as. So the equation you're actually given is exactly this one. It's F equals m delta v over t, with the m delta v being our change of momentum and over t being time. So force is the rate of change of momentum, and that's really useful when we start looking at safety features, so things like airbags, things like helmets. What these will do is, in this equation, they will actually add to the time it takes and the impact that you make. I say the time it takes in an impact. So we're adding time that as we have this cushion and the object is moving through this cushion, we're elongating that time. We're making it take longer for them to stop. And the longer we make it take for them to stop, the more we're going to increase this time, and therefore the less we're going to get in terms of force. So the less change in momentum over time we're going to get, and the less you're going to feel that impact. So things like airbags, crash mats, helmets, all of these are designed to add to the time of the impact, and that adding to the time of the impact reduces the force, and that's really important, really good. Reduced force means you're going to feel much better afterwards. So towards the end of this topic, we've got a couple of little niche areas we need to look at. The first is forces and braking. And in forces and braking, we need to understand what is meant by stopping distance, which is the total distance it takes for a vehicle to stop. We also need to consider why a vehicle stops and how the transfer of energy allows that to happen. So if we talk about that first briefly, the stopping of a car is quite simple, really. In the wheels of the car, it's got brakes. And when a force is applied from the brakes of the vehicle, to the turning wheel, work is done by friction force. So the friction force causes work to be done, and work being done is just a transfer of energy. So we've got a transfer of energy of kinetic energy, EK, into heat in this case, which is great, and it's a very effective way of stopping. However, of course, the greater the speed, or let's call it greater velocity, you need a greater stopping force for it to actually bring the car to a stop. And if you have a greater braking force, that can lead to a couple of things which are a bit of an issue. So it can lead to excess heat, so lots and lots and lots of heat, and it can also lead to a loss of control. And the loss of control of the car is obviously not what you want to happen. The examiners might expect you to know that sort of idea, that if it is going to be going very fast and braking too quickly, you might get overheating, stopping the brakes from working properly, or a loss of control of the vehicle. But on a stopping distance note, so stopping distance is made up of, this is the kind of a national view of stopping distances. When you go on to do some driving in the future, if you do, you need to look at the highway highway code, and the highway code talks about stopping distances and being aware of how long it will take you to stop. And you'll need to know that basically the stopping distance is the sum of your thinking distance and your braking distance, and if you add those two together, you get the stopping distance. Because to stop a car, you have to first recognise that you need to stop and think about the action that you need to take to stop, which is your thinking distance. That's the distance it actually takes your car will move for before you actually stop. And the braking distance then is the actual distance it takes your car to come from the speed it's going to an absolute standstill. And you can see that as you start going faster and faster and faster down this list, you can see that actually your thinking distance is always going to be fairly short. It is based on how fast you're travelling, but the braking distance makes it much more difficult for the car to actually stop, because it's got to dissipate all of that kinetic energy that it had. So it's got to get rid of all of this into heat, and do that quickly. So the other thing that we need to be able to aware of and be able to describe is the factors that will affect thinking distance and braking distance. And thinking distance is the things that are going to make you slow down your reaction speed. So one that is a big one is tiredness. So being tired is going to increase your risk of, increase your braking distance, your thinking distance. Sorry. If you are under the influence of drugs or alcohol, all of these things will cause you to have a larger thinking distance, as well as distractions. Distractions being the big focus at the moment is obviously mobile phones. Those will all increase your thinking distance, so the distance it takes for you to even realise you need to stop and to put your foot on the brake. The braking distance, however, is more to do with the quality of the car, so the condition of the car, and in the condition we need to really consider the tyres, so how much friction they can create on the road, how much traction they will get on the road, and the quality of the brakes as well. Brakes will get worn over time and get less effective. You've also got to consider there that the condition of the road. So if the road is wet or icy, the car will get less traction, less grip on the on the road, and so they'll be able to get less friction and therefore stop less quickly. We do need to know those. To add to the thinking distance, we do have a little overlap here with a reaction time experiment from biology, where you can measure human reaction times. This is the ruler dropping experiment. It might be worth just going over that to remind yourself, because you do need to explain how to measure reaction times. Thank you for watching, guys. I hope it's been useful. Please do watch more of my videos. Click subscribe and click like. See you again.